Okay, here we are, continuing with the review, questions 16 through 40. We'll see how far we get. So we are asked to deal with some complex numbers. So let's do this by hand, and then I'll also show you, if you forget, your calculator will actually handle this. So this is a subtraction problem, and we handle this just like we would any problem with sort of like terms. Is what we've got. So we've got 6 plus 9i. Just remove those parentheses. There's nothing in front to distribute. There's no exponent. Here, there's a negative in front, so it's got to distribute to both of these terms. So we get minus 9 plus 4i when we take out those parentheses. And now we combine like terms. So the number parts are alike. 6 minus 9 gives us negative 3, and then 9 plus 4i gives us a plus 13i. So we're going to put that in. Oops, sorry. We're going to go ahead and put that in. What was that? Negative 3 plus, 13i. I'm going to also verify that with the calculator, and I'll show you how you get your calculator to do complex numbers. First of all, we go to the mode button, and you want to make sure that your mode is, mostly the default is to be in real mode. We want to be in complex mode, which is a plus bi. We go over there and hit enter. Now that we're in imaginary mode, complex mode, it'll behave like it always does with being real mode. It just has new stuff available to us. Let's put it that way. And let me just clear this out. We can just enter this in as is. So parentheses, 6 plus 9. And your I, notice on your decimal point, above it is a blue I. That's the I you want. That's the imaginary number. It's actually there. Okay, minus subtraction. So again, notice there's two sort of negatives. This is just for the negative numbers. This is for the operation of subtraction. They are different. They operate differently. So make sure when you're doing subtraction, you use the subtraction key. 9 minus 4. Oops. 9 minus 4i. So this, the decimal was shifted. I get my I. And watch, we're going to get, it knows how to do imaginary numbers now. It might work without being in the mode, but if you do square roots and such, it's good to be in the complex mode. Minus 3 plus 13i. Okay, so if you forget how to do it, your calculator will remember for you. Yeah, 16. Let's go to 17. So here's another. We're going to square it. Again, you FOIL it out, but we can just do it here. 3 plus 9i, plus 9i. And then we'll square it. I'll come down and then just hit enter. Negative 72 plus 54i. Okay, I'm going to also do this by hand just in case you don't have the calculator that can do it. All right, so negative 72 plus 54i. So it works with the calculator. Let me just show. All we have to do is FOIL this out. Yeah, simple, right? Gotta remember. And you just treat the I as if it was an X, sort of, except the fact is that when we do get an I squared, we don't just leave it I squared because that is equal to negative 1. That's the imaginary number. We don't know what I is per se, but we do know that when we square I, we get negative 1. So we take 3 plus 9i times 3 plus 9i. That's squaring it. And so 3 times 3 is 9. 3 times 9i is 27i. Right? And then we get 9i times 3. That is another plus 27i. And that's 27 plus 27. That's the 54. This is the part that will throw most people look at. So 9 times 9 is 81. And then I times I is I squared. I squared is negative 1, right? We've got that over there. So this becomes negative 81. That's the, and then we've got this 9. So 9 minus 81, if you do that, you get your negative 72. And then 27 plus 27 is 54i. So either way works. Just remember, I squared is equal to negative 1. Check the answer. Of course it's right. Let's clear this off and go to the next question. Let's try to move along. But I want to make sure you solve the equation using the quadratic formula. Type in exact answer using radicals as needed to express complex numbers in terms of I. Okay, so all this stuff. So how do we do this one? So first of all, quadratic equations have to be equal to 0. To be able to use the quadratic formula, because that's how the quadratic formula is set up. It starts off equal to 0, and then quadratic formula says that your x is going to be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And so we solve this. So we're going to subtract 2x and add 1. We'll just do that, moving it to that moves it to the other side. So you get 7x squared minus 2x plus 1. So notice when they move to the other side, their signs change. And a is 7, b is negative 2, and c is 1. So then we put that in this formula, and that'll allow us to get the exact answer. So b is negative 2. So minus, let's go ahead and do this, minus negative 2 plus or minus, that gives us the 2 answers, potentially. B squared, so minus 2, with the parentheses around it, squared. So that's going to be 4. It's going to be a positive 4. Minus 4. A is 7. And C is 1. Looks like we're going to end up with a negative inside the square root, so we're going to end up with an I. All over 2 times A. 2 times 7. Okay. So negative and negative make a positive. Negative times a negative. So that gives us 2 in the front. Positive 2 plus or minus. This gives us 4. 4 times 7 is 28. Times 1 is still 28 minus 28. All over 14. 4 minus 28 is negative 25. So we get 2 plus or minus square root of negative 25. Come on. There we go. Over 14. Negative 25 is 5i. Square root of negative 25 is 5i. So we get 2 plus 5i over 14 as one answer, and 2 minus 5i over 14. Okay. Use a comma to separate the answers as needed. So we separate. Now I think they may want this to really have a complex number, they want the real part and the complex part. So you distribute this 14 to both. So 2 over 14 is 1/7, right? That would reduce. So I think what they're going to want is actually have this as 1/7 plus 5 over 14i, comma 1/7 minus 5 over 14i. Okay, so that's how we'll put it in, and it should make it all work out just nice. 1/7, I just use the divide key, plus 5 divided by 14 I, comma 1/7, arrow over, minus 5 divided by 14, arrow over, I. Let's see if that all works. This is what we got, right? Oh, your input is incorrect. I've just been saying it's, okay, what did it not like? Type an exact answer using radicals as needed. See, did I do that? Maybe I was too fast. It's 28. 28 minus 4. That's not 25. I just jumped to, 28 minus 3 is 25. So 28 minus 4 is actually 24. Okay. So 24, negative 24. So what do we end up with? We end up with the square root of 24 is just the square root of 24. So we end up with 2 plus or minus. So 2 over 14. I'll break them up. Square root of 24 over 14 I. So the negative square root of the negative gives us the I, and we're still got the square root of 14. So we'll get a plus and a minus here. And again, the 2 14ths, we'll leave it as 1/7. So my setup's really just fine. It's not 5 because it wasn't square root of 25. It's let's see if I can. Sometimes our minds just go, okay, it's easy, just do it. But no, 24 square root of 25 would be nicer, but it wasn't what it was. Sometimes we just are, that holy grail to get a nice number. Sometimes we fool ourselves. I fool myself. Anyway, there we go. Fortunately, now we go, okay, so just off by a little bit, but that's why that's important, okay? Hopefully that's good. You probably caught that and said, no, 28 minus 4, that's not 25. Little crow, what are you doing? Just trying to move too fast. Okay, find the coordinates of the vertex of the parabola defined by the given quadratic function. Now again, I'll show you 2 ways to do this. The coordinates are an x and a y. It says type in order pair, so make sure we'll do that correctly. You can find the x coordinate is minus b over 2a. b is 8, a is negative 1, so we get negative 8 over 2 times negative 1. Negative divided by negative is going to be positive. 8 divided by 2 is going to give us 4. So x equals 4. That's our x coordinate. To get the y coordinate, you have to plug that in for x. So the y equals negative 4 squared. It's the way, so the negative comes on afterwards. It's outside of this. Plus 8 times 4 plus 4. So that's going to be 16, negative 16. This is 32 plus 4, that's 36. And then you subtract off 16, that gets you to 30 to 20. So it's going to be 420. So that's how we do that one. And make sure you have your parentheses there because it's got to be an ordered pair. Now, you do have access to your graphing calculator. You can graph it and then find the vertex. So negative x squared plus 8x plus 4. Just graph it. Now the thing is, we know that, okay, yeah, it goes way up there. Oh, we still got something else. Forgot to delete this part or clear it out. Yeah. Let's come back. Okay, I don't see it. It's up there. So you could actually find it. I'll just show you. Go second calc. We're going to find the maximum, but you're kind of doing this. Oops, what did I do? Second calc. Maximum number 4. So we could do a left bound. I can see I'm to the left. It's up here. And then what I do is I just arrow up and I'm waiting. I keep going to the right till I come back down. Okay, there I am. I went up and down. Enter, and then I enter again. It'll give me my answer 4,20. But if you want, it's always good to get your window. We need a higher y value, so let's make it. Let's go to 40. I don't know. Again, you're just guessing, but just make sure it's high enough so that you can see it if you want to see it. Again, it gave us our answer without seeing it, but this is kind of nice. You can see it. Second calc. It's a lot easier to do all this. We want to find the maximum in this case. And so we do a left bound. We are to the left, hit enter, walk your little spider guy on over the mountain to the other side, and then hit enter for the right bound, and then do a guess, and it looks between the two. Oops. I didn't want to do that. I don't know what to do now. I'll just guess x is equal to, 4? Let's see how fast. Maybe it'll do it faster. It still took its time. Yeah, x is equal to 4, y is equal to 20. So it looks between there. There we go. Using the graphing calculator. Okay, let's check the answer. There we go. We're good. And I keep seeing that, and I didn't realize that an incorrect answer could look a lot like a correct answer because they don't change the color. I wish they'd do the incorrect in red. I almost missed it last time. So if I skipped over any, at least I'm showing them all to you. Okay, question 20 now. So use the vertex and intercepts to sketch the graph of the quadratic function given. Okay, and then do its domain and range. Yeah, you could find, again, we could go through the same process, but this is where I just say, using the technology, we have it, let's use it. It's going to be faster and more accurate. So x squared, and again, I was in financial planning for a number of years, and even if you can do some good judgment, you're good with number, that as my boss was, he still had a calculator with him, and you're dealing with clients' money. You want to have an accurate calculation. I worked with an engineer. He did the same thing. He says, I don't want to see your handwork. I want to see it run through a computer. We understand humans make errors. We do the planning, but we want to, as much as possible, run them through a computer. So let's go, actually, I want to go zoom standard. I don't know why, but let's just do it. Standard view. There it is. I can see it looks like it's crossing at 1 and 2, 3, 4, 1 and 5. A quick check, if you go second table, let's see this table set. I'll show you how to set up the table. So let's start at 0 and let's have it change, the table change by 1. Make sure it's set on auto, and it will give us an auto table starting at 0 going by 1s. There we go. Oops, that gives us the graph again. We'll go to the table, and we can see when x is 1, y is 0. That's an x-intercept. When x is 5, y is 0. That's an x-intercept. Gives it to us, but we could also use the tools on the graph. It doesn't necessarily give us our vertex, but if we're watching, it does look like, for symmetry reasons, it's halfway between 3, -4. That looks like a good call. Let's go back to the graph, 3, -4, and let's find, in this case, the vertex is a minimum. So 3, we do a left bound. Notice the spider guy is over here. We walk the spider guy to the other side, anywhere to the right. We'll hit enter, and then enter for a guess. And sure enough, it's 3, -4. I think I had that one. So there's our vertex. So now we should be able to graph this thing. Okay, so let me make it large. We're going to use this thing, and it requires us to put in 2 points, the vertex. And so the parabola tool, I come here, the vertex is at 3, -4. I think that's what you have to plot first. First time I've done this on this. And then you need, so let's plot that one. And then now let's come up. There we go. Hopefully I did 1, 0, or you could have done the other side, but that's what we're looking for. Okay, so let's save it. There it is. I've got it graphed correctly. The axis of symmetry, it goes right through the vertex. So that's always x equals what? In this case, 3. It's the x coordinate of the vertex. So that's the line that goes right through here. That's your symmetry. The domain for all quadratics is -infinity to +infinity. You can put anything, any x value in. And so let's use this one. And then we go a few less buttons to click on, right? Arrow over. There we are. There we are. Okay, so that's good. And then the range, well, the lowest y value is -4, and it goes up, and we can kind of see -4 is included. So we use a square bracket. These look like matrices. Let's see, do we have a square bracket? We don't. So I can't really use this one. It's not going to be, I think probably mostly for ordered pairs. But anyway, 4 is included, -4, sorry. -4, comma, and then go all the way to infinity, and then put a closing parentheses on that. Okay, so there we go. Those are our answers. Graph should be good, and yes, we're 100%. Okay, so 20. Let's keep moving along. Let me see, what time is it? Yeah, we'll keep going until we get to the, so hopefully get to 30, maybe get to 40. Find the zeros of the given polynomial function and give the multiplicity for each zero. Okay. To get zeros, we could graph it, which we will, but let me just show you 2 ways. So we're going to get to the graphing part. One way is to find zeros, we set it equal to 0, but we factor it first. So notice each of these has an x, so I can write this as x factored out, and then that becomes x squared minus 4x plus 4. And I set this equal to 0. So I know one of my zeros is going to be x. When x is 0, this whole thing is 0. But I'm going to get another one if this is factorable, which I believe it is. And again, I'm going to show you a method if you have difficulty with factoring. So that's going to be x times x. Right, that gives us x squared. What gives us 4? Well, that's either 1 times 4 or 2 times 2. This middle is 4, so I'm going to say it's 2. And this middle term says that it's negative. A negative times a negative is positive, so it's x minus 2, x minus 2. Okay, and if you FOIL this out, you'll see that that works. That this is this equals what we started with. So what I'm going to do, though, is x minus 2 times x minus 2 is actually x minus 2 squared. So that's about dealing with the multiplicity. So when we solve this, we get that x equals 0. That's one answer. X minus 2 equals 0, because if that's 0, then the whole thing's So we add 2 to both sides, and you get that x equals 2. Or you just look here, it's going to be the opposite sign, right? Now, because of the square here, that's got a multiplicity of 2. It's happened twice. And I'll show you from the graph what that looks like. That looks like that's a place where I call it kisses the graph. It kisses the x-axis. It's going to just, it doesn't go all the way through. This x equals 0, that has a multiplicity of 1 because it's to the first power. Okay, so the zeros are, well, we list them both. Use type integers or decimals, use a comma to separate. It doesn't want the ordered pairs, it just wants 0 and 2. Those are our 2 zeros. Okay. Determine the multiple. There is 1 0, the multiplicity of the 0 is this. There are 3 zeros, the multiplicity of the smallest. There are 2 zeros. We found just 2 zeros. The multiplicity of the smallest 0 is, then that's x equals 1 or x equals 0. That's going to have a multiplicity of 1. So I can put this in here. The multiplicity of the larger 0, x equals 2, is 2. There's really 2 zeros. It's like it goes through twice. And again, what it looks like, I'll show you a quick little graph of it. You know, what I can tell at this point is this is going to, at 0, it's going to go through, and then at 2, it's going to kind of kiss the graph, as I would say. So it's going to look something like this and then bounce back down because it's a cubic, and this is 2, this is x equals 2, and that's 0. Okay, not a beautiful drawing, but it works. Determine the behavior of the function at each 0. Select the choices. Okay, the graph crosses the x-axis at x equals 0. So again, this is what it's going to look like at x equals 0. It actually crosses. It touches the x-axis, or like I said, kisses the x-axis. A little sweeter way to talk about it. At 2, that's what it's going to be. And before we, that's the last answer. I just, pull up the graphs. Remember, you've got this tool. Go ahead and use it. So, especially if you've got difficulties in factoring, cool thing is, most of if it factors, it's going to cross at integer values, so it's going to be a nice graph. So you're going to be able to see it right away. The other thing is it verifies it because we see. Seeing is believing, right? Mostly. And watch this. Oh, I went the wrong way. It goes this way and then up. Yeah, I should have known that. But anyway, that's the other part is you have to examine. So it's sort of like mine, except mine is I did a reflection that doesn't exist. If it had a negative in front of the x cubed, that's when mine would have worked. But for the answers, it still worked. But I can see it goes through at 0 and it touches at x equals 2. And again, since they are integer values, you can go to the table. 0 is 0 and 2 is 0. So that's what it means. When they're talking about zeros, they're talking about y being 0, crossing the x-axis. Okay. Multiple ways to look at this. And you do the way that works for you. Let's check it. Yeah, we're correct. Okay. Let's keep moving along. I got about 15 more minutes, and I've got to take a break for a meeting, and then I'll come back and finish up some more. Write a polynomial function that imitates the behavior of the graph shown to the right. The dashed portion of the graph indicates that you should focus only on imitating the left and right behavior of the graph and can be flexible about what occurs between the left and right ends. So we don't know. It's doing some funky stuff here in the middle, but we know that the one end goes up, one goes down. What this is telling us is we have an odd function. So the leading coefficient is odd. So what we can do is we certainly anything, this 9x to the 4th, no way, that's an even. 3x to 6, no way, it's an even. So we've got this x cubed, and then we probably have one more down here, and x to the fifth. So is it x to the cubed or x to the fifth? Well, again, we don't know what's happening in the middle, but what we do is we look at the positive and the negative. Okay, so an odd power, let's just kind of review this in general. An odd is going to do, I call this my saguaro cactus with one hand up and one down. So notice if what would happen in general is x coming from negative infinity, y should come from negative infinity, and then it does this whatever and then it shoots off. This is your standard positive x to some odd power. Okay, if it's negative, it flips it, and that's what we got here. This is a negative x to some odd value. Okay, that's all that this is giving us. The first one is the one we want to choose. Okay, because it's a odd leading coefficient and it's got a negative in front. Okay, so even kind of does negative to negative, positive to positive. When you have a negative in front, it flips that around. So that's how we could do that. You could also graph these, and you'll see that this one matches. So if you couldn't remember this, hopefully you at least remember it's going to be odd, so you don't have to graph all of these. But you would see that the end behavior looks like this, and these both go in the same direction. I mean, you could just graph them all, that's fine, but this is the way you can maybe get to the answer a little quicker, and it's really what they're wanting us to be able to do. Oops, I didn't want to change my answer. Check it again. Okay, here we are at 23. So first we're asked to list all rational zeros. So let's go through that one. And then it asks us to use synthetic division to test possible zeros, but we'll just go ahead and graph. So rational zeros, we take the leading coefficient, which in this case is 1, and the constant term, which is 65. The factors of 65 are 1 and 65, of course, 5 and 13, because 5 times 13 is there. And again, each of these is a plus or minus, and they're divided by the factors of the leading coefficient, which are plus or minus 1. And so we can list all of these as 1, 5, 13, and 65, and each a positive and a negative. So we just go through and -1, +1, -5, +5, -13, +13, -65, and +65. So those will be all the possible rational zeros. Use here we go, and then we're asked to use synthetic division. Now that could take a while because we, these one of them is not, and so it doesn't give us the answer. So my suggestion on the test especially is to come and carefully put the equation in. And this is the second time I'm going through this one because I was not too careful, and I didn't see I didn't have a plus here, so it ended up multiplying 5x squared. So make sure you get it in correctly. Minus 61, not this minus, subtract 61. So there's all these, you have to have it in correctly. Minus 61x, and then subtract 65. Now, since we know the possible zeros are somewhere between -65 and +65, I'm going to go to my x window, and let's have the x's go from -70 to +70. So that'll handle any of these zeros, and the y. Let's go -40 to +40. We don't need to see up too high because we're looking at the x-intercept, but this will maybe help us. We'll see. We may want to zoom in, but okay, so we see one there, there. So we don't need to be way out at 65, obviously. So this must be like, what I've got, 13. It might be 5. Let's zoom in a little bit. So instead of negative 70, let's go negative 15 to positive 15. And maybe negative 20. Just zooming in to see things a little more clearly to positive 20. So there's that one. Now that's not an integer value. It looks like we've got a negative 1. 1, 2, 3, 4, 5, 6. Let's look at our table here. Our table set. Let's set this at negative 13. We'll go to 1. Change them by 1s. So when we come to the table, what we're looking for is where do we get zeros? None here. Not at negative 5. At negative 1, we certainly get 1. So we can put that. And nothing over here. Okay. So yes, this, I could find those other ones, and we will. Use synthetic division for possible rational zeros and they're different. One actual zero. One rational zero of the given function is negative 1. Okay. Now for these one, use a 0 from part 1 to find all the zeros. Now you could do it with synthetic division. I like to just do it here, second calc. Let's find the zeros. And to do this, it asks for a left bound, so we have to get over here. Notice we're at x equals 0, so I'm going to walk past it, but here we go. I jump from there to there, and now I'm at a left bound, right? So I'm down to the left, I hit enter, and then I'm going to walk it to the right. There, we're to the right now, and hit enter, and enter one more time, and I get a 0 at negative 10.3062. Do they say how many decimal places to use? They don't. Use a comma to separate answers. Needed to type an integer or decimal. There we go. Round it to 3 decimal places. Good. Negative 10.307. Comma. We know negative 1 is also a 0 because we see it there and we looked that one up. And then let's go find this 0 over here. Second calc. Number 2, 0. And I go to the right. I'm looking here. I'm at negative 8. I need to be at some positive x value. And I'll probably see, and notice y is way down there. There, okay, there we go. We pass through. I'm watching. X is going to be what, 7 or something. Y is coming up. It's down in the negative region. Here we go. There we are. So we're above. We need to be to the left. We're to the right of the point right now. So we come back to the left. We don't see it, but we'll hit enter. We're down at negative 28. We hit to the right. We're to the right of the point now. We hit enter, and then we just hit enter for a guess. It looks between the two. This is a 0, right? 10 to the negative 11th. So there's 10 zeros and a 1 point. 10 zeros. Okay, so this is 0. 6.307. 6.307. So you see some symmetry here. 6.307. Okay, So that should do it. That's the way I would do it. They don't really say find all the zeros. But again, you could use synthetic division, but it would take more time. So we got correct. Okay, so, but know how to find the rational zeros. It's the ratio of the first coefficient and the last constant term, all the possible factors of those numbers. All right, let's look at the next one. Here we're supposed to find a function that fits this situation. We have n equals 3. So what we can write with what we have is our function has to be of the form f of x, some potential number a times x minus the first 0, x minus the second 0, and x minus the third 0. Okay. First 0 is -2, so as we put that in, minus a -2 is going to be plus a 2. And then we get, now when we have a imaginary, there's a theorem that states it, we also have its conjugate. So we've got 5 plus 2i, and we get 5 minus 2i. That's the conjugate. Okay, so then we get minus 5 plus 2i times x minus 5 minus 2i. And that's what f of x is. Now we're going to figure out what a is. That's what we use this point here. Okay, so let's go ahead and expand this. Do we need to? It'll help, I think, if we multiply these out. So we get an x squared here, x times x. We get an x times -5. And then we get an x times 2i. Then we multiply the -5 times everything. So -5 times x gives us a -5x. -5 times -5 gives us a plus 25. And -5 times 2i, I'm going to write it down here, we're running out of room, is -10i. So we've taken care of that. And then we multiply -2i times everything. -2i times x gives us a -2ix. And this is the beauty of conjugates, is the i's are supposed to, when you multiply them, they're going to cancel out. A -2i times -5 gives us a positive 10i. And then a -2i times a positive 2i is -4i squared. However, I squared is -1, so we're going to get a plus 4 there. But before we do that, let's combine like terms. Got a -5x and negative, so those will combine. But notice this, we got a plus 2ix and a minus 2ix. Those are 0. We have a -10i and a positive 10i. Those are 0. Let's what we were hoping for, getting rid of this. And then this becomes a plus 4 because negative I squared is equal to, or I squared is equal to negative 1. So you get negative 1 times negative 4 gives us a plus 4. So we got plus 25. That's going to give us a plus 25 plus 4 is 29. Negative 5 gives us a negative 10x. And then, that's x squared. Sorry, I said it, but I didn't write it. So we got x squared. So that's that part. And this first part is going to be x plus 2. Type an expression using x as the variable to simplify your answer. Okay. Okay, and I guess that means multiply it out. We could figure out what a is at this point, or we could just multiply it out. Let's go ahead and multiply it out. X times x squared gives us x to the third. X times negative 10x is negative 10x squared. And then x times 29 gives us a plus 29x. Then we've got 2 times x squared plus 2x squared. 2 times negative 10x is negative 20x. And then 2 times 29 is 40 plus 18 is 58. Running out of room here, but that's okay. And then this is all times a. And let's see, do we have any like terms? We do. We've got a squared. So our function is going to be a times x to the third, negative 10 plus 2, that gives us a negative 8 x squared. The x 29x and negative 20x, that's going to leave us with a positive 9x. And then a plus 58. Now this f of 1 equals 60. When we plug in 1 for x, we get 60. So 60 is our answer when we plug in 1. So 1 cubed is 1. 1 squared is 1 times negative 8 is negative 8. 1 times 9 is 9. And then we've got our plus 58. So let's see what this gives us. This gives us negative 7. 9 will be positive 2 plus 58 is 60. So we get 60 equals a times 60. Divide both sides by 60. A is 1. So that's kind of nice. So this here is our answer. Let's go ahead and put that in there. And I think that's all we need to do. X cubed minus 8x squared plus 9x plus 58, and that'll be our answer. Okay, so again, use this basic setup. If it was a fourth degree, we'd have another term here. It's x minus the zeros. Plug in the zeros. Go ahead. Let's check our answer. Yeah, it worked. Okay. Put that there. Let's keep moving forward. Let's remove the work. So 25. Find the vertical asymptotes, if any, in the values of x corresponding to any holes if they're ratio. So do we have a hole or do we have an asymptote? So this x plus 3, x. So this is factored for us, which is nice. Thank you. There are no common factors between the numerator and denominator, so nothing's going to cancel out. There are no holes. You could go ahead and graph this if you'd like. What you'll see is that there are holes whenever the denominator equals, not holes, there'll be asymptotes wherever the denominator equals 0. So we can use our product rule whenever you're multiplying two things that equal 0. One is 0 or the other is 0. So x equals 0, there's one asymptote. X minus 6 equals 0. Add 6 to both sides. X equals 6 are two asymptotes. So vertical asymptotes are blank and whole. Of course, there are no vertical asymptotes. Yes, there are. The vertical asymptotes are blank. There are no holes. So I would say there are no holes because there's not a common factor. Had there been an x plus 3, that would have created a hole in the denominator. But this is what we're going to do. And they say, what? Separate them by commas. There we go. Let's check our answer. Oops, it didn't like it. What did I do wrong? 0. The vertical asymptotes are, they probably, okay, type an equation. Okay, read the instructions, little crow, and then use commas to separate them. So it's a formatting error. It should be, and again, this one is my fault. They told us how to do this. Write an equation, x equals 0 and x equals 6. Those are the asymptotes. I'll put maybe a space there. I don't know if that's important or not. Now let's check it. Okay, see, it's happy. Had the right answers, but they wanted, and that makes sense. Asymptotes are vertical lines. You need to have x equals. Okay, let's go to the next one. Let's get at least a 30. And here's, let's clear this out. There are no horizontal asymptotes, are there? So again, what we look is in the numerator and denominator, are they like factors? They are not. The numerator and denominator are not like factors. They don't cancel out. So we will get an asymptote whenever the denominator equals 0. So we'll subtract 4 from both sides, giving us 3x equals negative 4. We will divide both sides by 3, giving us that x equals negative 4/3. That's our equation. Type in equation, simplify your answer. See, so it says it right there. We will do it this time. X equals, not plus, equals negative 4 divided by 3. Use integers or fractions. Oops, why does it not like that? Subtract the 4. Oh, horizontal asymptote, not vertical asymptote. Okay, we'll leave this one. So horizontal asymptote, again, sorry, I'm just trying to get through these. It's been a long day already, but we'll keep moving. Horizontal asymptotes, okay. There are 3 possibilities, either y equals 0 if the denominator is larger than the bottom, the degree. This is not the case. The degrees here are equal, right? They're both to the first power. It's easier than said, okay? So, but you could have it if the bottom had a larger degree, then it'd be y equals 0. If the top is larger, then there is no horizontal asymptote. If the degrees are equal, then this will behave like minus 5x over 3x. The x's canceled, and so this is going to behave like minus 5 over 3. And they want an equation, so a horizontal line is y equals negative 5/3. See, we're pretty close, but we were giving them the wrong thing. We had negative 4/3. It's actually negative 5/3, but it's a completely different thing. It's y equals, it's a horizontal line, minus 5 divided by 3. There we go. Now they're going to like us. Yeah, that's good. Read the questions. Okay, so read carefully, prepare yourself. But again, doing this practice, this review, it's going to be very beneficial to you. Okay, let's take a look at 27 here. I'll follow 7-step strategy to graph this. Hey, you know, do the little crow 1-step strategy. Let's plug this in the graphing calculator. But this time, little crow, don't forget the negative. I went through this. I did a great job, but I forgot the negative, so all my answers were wrong. Let's walk through it together. I deleted that part. I didn't want you to have to go through all that. You would probably seen it, but what we do, come to y equals, yeah, see, I forgot my negative. So I'm going to put that negative out front, and I'll change my 1 to a 4, so that's a little different. Now, actually, let me clear this. I need to show you something, because they're going to want everything in terms of fractions, which are doable. You'll be able to plug the numbers in. But what's really cool about this, the F1, so that's a green, so alpha. If you do alpha F1 with the TI-84, the latest system, operating system, it can actually, you put this in as a fraction, numerator over denominator. So we get that template. We put in 4, and then we put in x squared, but this, be careful, because I did this last time and I forgot to put the negative out front. Deleted about 20 minutes worth of work or whatever it was, but that's life. So we put our negative out front. There we go. But now, when we go to look at answers, or like the table, the second table, we get our answers as fractions. That's what we want to see. Okay. We can also go to the graph. So this is going to answer a lot for us. It comes down like this, goes up like that, goes there. Now we look at the denominator, x squared minus 9, that's x plus 3, x minus 3. So that's where we're getting these asymptotes. When we look at the table, we see at negative 3, there's the error. That's a vertical asymptote. And positive 3 is going to be another vertical asymptote. So everything's there. But let's go ahead and do step by step. It is symmetric by the y-axis. The y-axis cuts it in half. If you were to fold it over, it lands on itself. So we could say it's got y-axis symmetry simply from the graph. You could also do it by looking at all this stuff. What is the y-intercept? Well, the y-intercept is when x is 0. So you plug in 0, it's going to be negative 4 over negative 9, which is positive 4/9. And we see it right there. And when we go to our table, we see when x is 0, we get 4/9. Okay, that's cool. 4/9. What are the x-intercepts? Well, there are none. There's no places where y equals 0. Again, partly because I don't want to go there. I want to go to the graph. The denominators, the degree of the denominator is x squared. It's x to the 0 on the top, so the denominator has a larger degree, which means that the horizontal asymptote is going to be y equals 0. Okay, so there are no x-intercepts. Vertical asymptotes, again, as we spoke, plus and minus 3. You could get that from the table. You could see that on the graph. You can also factor the denominator and find where we got the zeros. So we get x equals negative 3 and x equals positive 3. So vertical asymptotes. Horizontal asymptote, well, we get 1 at y equals 0. And again, that's because the degree in the denominator is larger. Now we can start filling in these values. Negative 8. We come back here to the table. And again, you could put the negative 8 in for x, square it, 64 minus 9. You could do all of this, or I like to just come here to the table. Negative 4 over 55. Negative 4 over 55. Negative 5, we get negative 1/4. Makes sense, right? I think. At 0, well, we've already looked that one up, but what that is, 4/9, positive 4/9. And then over here, since it's symmetric, we're going to get these same answers. And again, they are negative, so at 5 we get negative 1/4. And then you could do it by hand or just like I'm doing, the table. And negative 4/55. And then now we just need to select the graph. We'll take a quick peek here. It's just a little bit above, but down here, these, you know, the asymptote goes to 0. So it looks like B, certainly not C. This is crossing the x-axis. This is too far up. This is below the x-axis here and going down. It's B. Okay, so B. Take a quick look. See, let's and then now let's check our answer. Now we're okay. I did all that work. I forgot the negative the first time. Sorry about that. Okay, so that goes there. Clear it out. Just keep plugging forward. So 28. We got a few more to go. Begin by graphing 2 to the x, then use the transformations of this graph to graph the given functions. Okay, so what we see is whatever 2 to the x is, we're going to go up 1, so it's going to be 1 higher. And then there's also a horizontal shift of negative 1, so it's going to go in the positive direction by 1. Right? So those are the transformations. Does not reflect about the x. Nope, there's no negative on the x. It does not stretch. It's not shrinking. It's just a shift upwards, not downward. A shift unit to the right. Which of these? Yeah, it does go to the right because a negative, we're subtracting 1, so that actually moves it 1 in the positive direction, which is the right. That's the only one. Let's see what else. Shrink horizontally. Nope. Reflect about the y-axis. Nope. No negative on the outside. Shift 1 unit upward. I missed that one. So that does happen. And that's all that's going to happen. No stretches because we're not multiplying or dividing. And we're not going to the left. We're going to the right. We don't reflect. We don't stretch. We don't shrink. We go 1 unit up, not down. So that's it. So graph this in its asymptote. Give the asymptote as a dashed line. Okay, so let's come here. You plug in a few points. I say let's just go here, go to the graphing calculator. Let's plug it in. Let's clear this out. Let's go 2 raised to the x minus 1. And then we add 1. Let's just do it. And then we go to the graph so we can see what it looks like. So it is up here. It looks like a horizontal asymptote, not at 0 because it's been shifted up. It's going to be at y equals 1 is where we have the horizontal asymptote. And then if we need to, usually the graphing tools, we have to plot some points. So we've got some points to plot here, maybe 1, 2. Okay. Let's see, let's move this over here. Let's see how we can graph this. So we want to do a dotted line for the horizontal asymptote, and that's at 1. How do we do that? Let's go with this, a dotted line, right? So horizontal line here to there. There we go. And then we want to do the J-curve exponential tool, and the way that's going to be the solid one. And we've got a point 1, 2, and then 2, 3. 1, 2. Really? How did, oh, that. Let's see. Base of 2. Okay. We're not going to stretch or shrink. We are translating. to the right, and vertical translation 1 up. Now I need to take this and move it down there. I don't know why that did that. I wasn't paying attention. So there's our horizontal asymptote, and then it looks like we've got everything good there. Let's save it. Okay. We've done that part. We've graphed it now. Find the equation of the asymptote. Okay, well, because it's shifted up, the asymptote would have been y equals 0. It's now y equals 1. Does that make sense? Let's see, how else would we look at that? Yeah, put in 0 for, that's just this, yeah. Exponentials, 2 to the x, it would have been 0. So it just got moved up. Observe the graph and find the domain. Well, the domain is everything. It goes from negative infinity to positive infinity. No problems with exponentials. So we put that in there. Let's go ahead, interval notation, minus infinity until positive infinity. How about observe the range? The range, okay, the lowest value would be 1, y equals 1. But 1 itself is actually not included. So we'll put a parentheses, and then it goes all the way, shoots all the way up to infinity. Let's see what's going on here. Maybe I need to get inside there. Okay. And I think that should do it. Oh, 80% it didn't. It's my formatting. It's this thing here. Get it in the right place. Now, on the exam, if I look over, I try to look over all of them. If I miss them, let me know. But I can see these types of things, formatting errors. Yeah, now we're at 100%, but try to watch for those. Okay. And I know these videos are long, but it's so write the following equation in its equivalent logarithmic form. Okay, so this is an exponential. What we want to do is write as an exponential. It's really a cubic is a 1/3 power. So let's go 125 to the 1/3 power equals 5. This is what I like to call the log dance. The base of an exponential is the base of the logarithm. So this is going to be log base 125. And then what happens is the exponent becomes the answer, and the answer becomes the input. That's what we write. Log of base 125, 5 equals 1/3. Just a dance. Let's see, how do I do this now? So then I got this guy, 125, arrow over, 5 equals 1/3. Type an equation. We did. Okay, so it's just the dance. The base is the base. The base stays the base. And then the exponent becomes the answer. The answer becomes the input. That's how we do those. I just call it the dance. So it's already correct. Let's go to the next one. Getting there. 30. Finally, we made it. Without using a calculator. Okay, well, you could use a calculator. I don't care, but we can also do this. This is 4 log base 4 of 4 to the 1/2, right? Log base 4 of 4 to the 1/2, and then because the bases are the same, 4 and 4, the answer is the exponent. It just is. That's a property we have. So when you see that, you get them the same, and so 1/2. Just like that. Clear. 31. Let's see how. So begin by graphing log base 5 of x, and use the transformations to do all this. And look at, not a lot going on. It's just a translation inside we're adding 6 inside the function, so that's going to move it 6 in the negative direction, 6 to the left. That's all that happens. Nothing else. Nothing else is happening between these two. So shrink horizontally, shift 6 units to the right. Nope, we're going to the left, 6 to the left, and that's it. Okay, no shrinks, no reflections, no stretches, nothing. We're not going up or down. We are just going to the left 6. So then now let's graph it. So we click on our tool, and what does our tool let us do? We want to do the exponential graph, and again, we'll put our line. We're doing a vertical line, and usually a logarithm is at 0, right? And we're moving it 6 to the left, so it's going to happen here. Vertical line goes there. Then we got this guy going. Let's see, what do we do? Selected logarithm tool. How do we use this? What do we do? Do we just click? Yeah, we just click. Oh, but we want that to be solid. That's good. And again, okay, so now vertical, horizontal shift, horizontally shifting it. We're going to go to the left, so we'll do -6, right? That should do it. Nothing else needs to happen. And that's all we need to do there. Let's see what else. What is the vertical asymptote? The vertical asymptote is x equals -6. What is the domain? Well, the domain are the x values, so there's nothing below -6. There's no graph here, so it's -6 and forward, and -6 itself is not included. So it said x plus 6 has to be greater than 0. That's what the domain is. So we get from -6 all the way, come over a little bit more to infinity. There we go. That's good. What is the range? Well, the range, it shoots all the way down to -infinity, all the way to positive infinity. So infinity to infinity, -infinity to positive infinity. Do 2 little right arrows, and there we are. And that should do it. 100%. And again, practice these, goes through these. If you need to, you can graph these on your graphing calculator. And just let me show you for a log. There's 2 ways to do it. With 84, there's actually something called log base. You put it in, but let me just show you. If you needed to graph this particular one, and you didn't, you could do the change of base. So you could use like base 10. So what we do is we would put log x plus 6. That's actually a log base 10, right? Got an extra parentheses in there. And then we would divide by log of 5. This is the change of base. Okay, so it allows us to use a base 10 as if it were a base 5. And then we could look at the graph, and there it is. That's exactly what's happening. 1, 2, 3, 4, 5, 6 is where the vertical asymptote is. And if you come here and look at your table, watch what happens at -6. We get our error. It's undefined at -6 and anything below there. So that also helps you spot the domain this way. You use your tools. 32. Okay, use property of logarithms to expand this logarithm. So there are 3 properties of logarithms that are of importance. Multiplication becomes addition. So remember this one, log of x times y becomes log of, and again, whatever base b, x plus the log of y. When you're dividing, log of x divided by y becomes log of x minus log of y. And then if we had log of x raised to the y comes down in front and becomes multiplication log of x. So those are the three main rules we use. And for this logarithm, we want to recognize a square root is an exponent. It's a 1/2 power. So this is log of base g, a to the 1/2 times b to the 6th divided by c to the 8th. So we got multiplication on the top and division by c. So I like to just do these three. So this is going to be a plus and this is going to be a minus. Anything in the denominator gives us a minus. Think of it as negative exponents, right? Log base g of a to the 1/2 plus log base g b to the 6th minus log base g c to the 8th, and then bring down the exponents in front. So you get 1/2 log base g of a plus 6 log base g of b minus 8 log base g of c. And that's all we got to do. We've got it simplified as far as it'll simplify. And let's just type that in there. 1/2 log base log base g. And I've seen some questions about entering logs. This log, natural log is ln, and notice how when it recognizes as a log, it becomes bold. If it's not becoming bold, it might be you're entering the wrong letters. And all I can guess is that you're entering a capital I in. It's a lowercase l when we use natural log. Okay, this is a plus 6, and watch, if I do, that's a capital I, little n. Notice it doesn't become bold. If I do a little l, capital N, now it becomes bold. Okay, that's all I can figure out. But we don't want natural log here, we want log log. And then it recognizes it as a function, and then we put that there, and we do our g arrow over, and then that's b. Right, b. And then we subtract 8 log, and then we put our little base down here. That's g, and put c. So that should do it. You could put parentheses around the a, b, and c's, but I think it'll be okay without it as well. Let's check it. Yeah, it's okay. (33) Solve the following exponential equations, express the solution, set in terms of logarithms, and so forth. Okay. You could do this with a graphing calculator. You could graph one side is y1, the other is y2, find it, and we're good. We could also use logarithms. So we take the natural log, ln of both sides. Okay. When you take the ln, the exponent comes down, and so you get 1 minus 4x times the natural log of e equals the natural log of 1147. Now the natural log of e, I guess we should go like this, is equal to 1. Natural log of e is 1. So we get, what do we get? We get 1 minus 4x equals natural log of 1147. So we solve for x, subtract 1 from both sides, subtract 1. You get negative 4x equals natural log of 1147, subtract 1, and then divide everything by negative 4, right, both sides. That'll be our answer. That's what x equals. So the solution set expressed in terms of logarithms is, use a comma to separate answers as needed. Well, there's only one answer. And that's what's the nice thing about exponentials. They just, that J shape, you're only going to get one answer. And they want it in terms of logarithms, so they don't really want the numerical value. So this one, and now notice that is natural log. If I go capital I, this is not going to, it won't count it as correct. You need natural log, log natural. 1147. And I guess it will figure it out, but let me do this. I just feel more safer. It's a natural, that's what's in the natural log. The -1 is outside it. And then what we really need to do, I guess I should have done this first, is, let me select it. Let's see, what if I go like, yeah, maybe I'll have to retype that. It's a shame. Yeah, let me put a big parentheses. We'll do it this way. Parentheses over the whole thing, divided by, there we go, -4. That should work. Now I use a calculator to obtain a decimal approximation for the solution. Okay, so we got to use the calculator anyway, but we did have to be able to also solve it without the graphing calculator. Let's go here. We could just now plug this in. We go with natural log 1147, subtract 1. That's the answer. And then we divide that by -4. So we get -1.51122. Now use a calculator, comma, round to 2 decimal places. Okay, that's always important. -1.51. That's 2 decimal places. No need to separate by a comma. There's only going to be one answer. And we are correct again. 7 more to go. Solve the following logarithmic equation. Be sure to, okay, the best way to solve these is using that log dance. Okay, you can exponentiate. You can do what you like, but when you've got this logarithm, we do the log dance. So we're going to change it to an exponential. The base of the log becomes the base of the exponential. The answer to a log becomes the exponent, and the input of a logarithm becomes the answer of the exponential. Now 2 to the 5th, that's 2 times 2 times 2 times 2 times 2 times, times itself 5 times, that's 32. So we get 32 equals 7x plus 8. Subtract 8 from both sides. You get that 7x equals 6 from 30 is 23, right? No, 24. 24. 32 minus 8 is 24. And we divide both sides by 7. So x is equal to 24/7. As an integer or a simplified fraction. Yeah, that's all we can do there. 24 is not divisible by 7. 28 is, but not 24. 24 divided by 7. If I did that right. Oh, I didn't like that. What did I do wrong? So 2 to the 5th is, 2 times 2 is 4, times 2 is 8, 2 is 16, times 2 is, so there's 32. 32 minus 8, 7x plus 8. Solution set. Not infinitely many, no. There is, oh, I must have clicked on there. I entered it there. Now let's check. Well, the answer was correct. I just did a stray little check mark. there. Okay, let's go to 35. Solve the logarithmic equations, so such and such. So first thing what we'll probably do is get this to be one logarithm, and then you get a log equals a log, and it basically gets to cancel it out. So let's see how that works. Okay, so we've got two logarithms here, but it's by addition, so that means it can become log of x times x minus 3. Right? We can rewrite using log properties, double parentheses, equals the log of 28. Now, because logs are one-to-one functions, if the outputs are equal, that's what this says, the log of this equals the log of that. If the outputs are equal, so are the inputs. The inputs have to be equal. That's the only way. That's what a one-to-one function tells us. I'm going to take this x and I'm going to distribute it through. So x times x is x squared. X times negative 3 is minus 3x. And that has to equal 28. Subtract 28 from both sides so that we get it equal to 0. Notice the logarithms are gone. And the way we can go about this, again, you could graph this and find its x-intercepts because that's where it'd be equal to 0. The other thing you can do is you can factor this. 28 is 7 times 4. If you subtract from 7 from 4, 4 from 7, you get 3. So it works to factor. We got x times x. We're going to have 4, and we're going to have 7. It's negative, that means we're subtracting. This negative in the middle means the larger number is going to be negative. So we've got to do that. So that's all those rules for, we get that. And so we're going to get x plus 4 equals 0, or x minus 7 equals 0. Okay. If you couldn't factor, you can always, again, graph it. You'll find either from the table that negative 4 and positive 7 are your zeros. You get there a little bit quicker. So yeah, subtract 4 from both sides. You get x equals negative 4. Add 7 to both sides. You get x equals positive 7. So those are our two, that's our solution set. Let's go ahead and put it in. And that's how we solved it. Negative 4 and 7. And don't check on anything else. Oh, what did it not like? Solve the equation, find the solution. Oh, yeah. Step back, little crow. Now, are both these answers valid? Well, you can't put, they're not both in the domain. No, so I put negative 4. No, wait, that's not going to work. A log of negative 4, no, can't have negatives inside a logarithm. So while we get those two answers, that's why maybe graphing solutions are better. We only got one answer that's going to work. So we got to remember to do this. See, let's stay there. Okay, now we're going to be okay. Okay. Five more. Okay, we've got this formula that's given to us, describes the accumulation of values, explains it all. So then we were supposed to calculate how many, what's t going to be? Okay, so we got the amount invested, we got the annual interest rate, and we want to double the amount invested. Well, to double 6,500, you got to multiply it by 2. That's 13,000. So we want to figure out, when do we hit $13,000? How long is that going to take? Okay, because that's double this. So we use this formula here. Get 13,000 equals 6,500. That's our principal. That's our accumulated value. E to some interest rate. No, we're given an interest rate, 11%. So it's 0.11. Come on, give me my decimal. And the time, we don't know that. That's what we got to find out. Okay, go to solve this. This is 6,500. 13 divided, that's 2. You could jump to this a little easier. E to the 0.11 t. And like we did the last time, we just go ahead and take the natural log of both sides. The exponent comes down. Natural log of e is 1. So this is natural log of 2 is equal to 0.11 t. Again, natural log of e, but this part is 1, so multiplying by 1 is that. So now we just divide both sides by 0.011. 0.11. That's what t is going to be. And do they want, do not round until the final answer, then round to 1 decimal place as needed. So this one we can just go ahead and calculate away. Natural log of 2, it's the doubling, divided by 0.11. 6.3 years. 1 decimal place, right? 6.3 years. There we go. Okay, we're almost there. So again, using an exponential, paint contain 1% of the original carbon-14. Use the exponential decay model, carbon-14 of this, to estimate the age of the paintings. So we don't know what we started with, but we do know that we ended up with just 1% of what we started with. So this kind of gives us the half-life, you know, it's decaying, or comes from the half-life, but that's not what we want. What we had, so let's just, so 1%, let's say we started with 100. We now have only 1. So instead of we start with 100%, we only have 1%. So 100, and now we have 1. Okay, so that's kind of the way to think of this thing. Or we had 1,000, then we'd have 10, you know, however you want to do it. But what that gives us is it gives us a way to think of this formula. Oops. 0, 0. There's a decimal there. And then there's 3 zeros. 121. And then there's a t. Okay. So we divide both sides by 100. So that's going to be 1/100th or 0.01. So that's it. That's the 1%. Okay. E to the negative, because it's decaying. 1, 2, 3, 121 t. Take the natural log of both sides. Right? And that gets the exponent to come down in front. Natural log of e is 1. So then we get natural log of 0.01 is equal to negative 0.000, 3 zeros, 121 t. That's what we divide by. And they want an approximate answer, round your answer to the nearest integer. So we just go ahead and do it. Oops, let's come here. Natural log 0.01 divided by negative 0.123, 121. Wow, about 38,000 years old. That's a pretty old thing. This is how they do let 38,059 round to the nearest integer. So we leave it at the 9 because it's a 2, so round it to that. And that should be good. 100% good. Now use the property of logs. Remember there's only two properties, but this time we want to put them back together. So addition becomes multiplication. But before we do that, we want to take this multiplication in front, turn it to an exponent. Okay, so the first step with this, as we put basically back into a single logarithm, take any things that would become exponents and put them up there. So we get natural log of x to the 1/6 plus the natural log of y, and now we can multiply these. We get a single logarithm with x to the 1/6 times y. That's it. That's as simple as we can make it. So again, watch your what you input. It has to be the lowercase l, lowercase n. That's the natural log. I'll go ahead and put that parentheses. We raise it to the 1/6 power and 2 enter so that the y is down on the line. And that's what we got. There we go. Okay, down to using some synthetic division. Simplify your answers. Do not factor. Use integers or fractions for any numbers in the expression. So let's go through. So we're going to divide. Let's go with blue. Okay, so let's see. We'll come over here. So we're taking 3x squared, 3x cubed. Come on. Okay, you got 3x cubed plus x squared minus 4x plus 6. And then we're going to use the division. We're going to go with x minus 3. So what times x gives us 3x squared? Well, that's going to be our 3x cubed, 3x squared. 3x squared times x gives us 3x cubed. And then 3x squared times negative 3 is going to give us negative 9x squared. Right? Okay. I'm going to switch to red. We subtract, so that makes this negative and this positive. This is now 0, which is supposed to happen. That's what we're trying to make happen. And this part, we have 1 plus 9, so we end up with 10x squared, like terms. So what multiplies to give us 10x squared from an x? That's going to be plus 10x. 10x times x gives us 10x squared. 10x times 3 gives us a minus 30x. All good. Again, we subtract, so that changes this and this. This is 0, and we get negative 4. I guess you could bring that down. That's typically what they do. You could leave it up there, whichever you want. So negative 4 from 30 gives us a 26, positive 26x. I guess, yeah, then bring down the 6 all the way, right? Makes it easier. There's a better way to do it. So we're going to multiply by 26. So 26 times x gives us 26x. 26 times negative 3 gives us negative 78. Let's go ahead and subtract. I like to do it this way, minus, and then that becomes a plus. So this is 0, and then we get 6 plus 78 is 84. That's the remainder, and so it's this, and the remainder 84 over x minus 3. So let's see how that works out. Put our remainder of 84 and 3 x squared plus 10x, not s, x plus 26. Check our answer. Hey, we made it. So beautiful to see that it's all correct. And again, it's just tedious to go through, and it's so easy to make arithmetic errors as we go through it, but pace yourself, keep focused, you'll do well. You'll do well. Practice. Go through this. You're getting yourself really well ready with these. Last question now. Complete the table to the right for the half-life of a certain radioactive substance. So they want the decay rate. The half-life is 4,380 years. If you sort of remember, there's an easy way to do this, but I'm just going to start from scratch because, you didn't remember it. Where would we start? Well, radioactive decay is that some future value, and what we're going to have is we're going to have half left over, right? So whatever we started with is 1. What we're remaining is going to be a half. Starting off with 1. It's always a continuous radioactive substance, continuously decaying. And again, we get some. So we went from 1, we got half of what left of what we started with, and there's a constant, and there is a time. K is our rate, right? K is our rate, and we get half of it after the passing of 4,380 years. So what do? Well, we take the natural log of both sides, because that's going to get rid of the e part for us. So natural log here, natural log here. The exponent comes down, and natural log of e is 1. Okay, so if you've memorized it, it's going to be natural log of 1/2 equals, I'll put the 4/3, we got a variable k, we put the number in front, 4,380 times k. Natural log of e is over here, but that's just 1, so it goes away. And then we divide both sides by 4,380. So again, it's just the natural log of 1/2 divided by the number of years it takes to have that happen. Now, if you remembered that, great. And maybe by the time you do this a few times, you'll remember it for the test. We just need to put that in, rounded to 6 decimal places. But if you can just at least remember the exponential decay. And if you can't, remember it was in here during the test. They gave that formula for us. So that's what I try to do, is show you things that'll be made available to you. So we just go here, and we take the natural log of 1/2 or 0.5 if you want. That's maybe a little easier way to enter it. And then we're going to divide that by 4,380. And that again gives us our constant. It's 4 decimal places. So they want 6 decimal places. So this is going to be a negative. Again, it should be negative because it's the rate is it's a decay rate. Okay. So it's going to be, well, let me write it out here while I'm here. So what this is 10 to the negative 4. So this moves it back 4 places. 1, 2, 3, 4. So let me negative 1.5825278. Okay, so we're going to move this decimal place 4 places. So it's 1, 2, 3, 4. So the decimal place comes here, and there's going to need to be 1, 2, 3 zeros. Put the negative out front. So negative 0.0001, 2, 3. So we need 6 places. 1, 2, 3, 4, 5, 6. We're going to stop here. Look at if we need to do any rounding. Well, 2 is less than 5, so we leave the 8 and 8. Don't have to round it up. It's called rounding down, but doesn't mean we change the 8. So we're going to put in negative 0.123158, and we're done. That's 6 decimal places. And see if we're, check our answer. 100%. We're good. That's question number 40. So we are completed. We made it all the way. I guess, let's see. I don't really have my camera set up anymore, but I'm going to post this, and I wish you the best of luck. Go over this practice test multiple times until you feel fairly confident with it. You know, the 20 of these questions, 20 of these type of questions will be on the exam. So go through 40, focus, 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 get these down, be able to do 20 of them. Take your notes as you go through, reviewing your notes before you go, set them aside, and then on your scratch paper, as soon as you start the test, write down what you can remember. Write down formulas. That's how you can bring formulas in, is it's got to go, whatever's in your mind, you can use. And the idea is that if you do it at the start of the test, if you sort of start writing down what you remember, it'll probably be clearest at that time. Once you start doing the test and doing questions, that's when we tend to get, things get mixed up a little bit, and we start, you know, that's what we forget. But if at the very beginning, you just study your notes real carefully, maybe I prefer to get it down to half a page or page at the most, stuff that you can remember. Study, study, study. Set it aside. Get the test open, go through all your, you know, the RP Now stuff, get ready to take it. And then the first thing, before you even start that first question, on your blank pieces of scratch paper, write down the important formulas that you've struggled, that you know you'll be needing, the principles, whatever it is, whatever's on that half sheet of paper that you memorized, write that down. It's called a memory dump. It's there for when you need it. That's how you bring notes in, legally bring notes into the test. Okay? And you'll do well. Remember to breathe, pace yourself. You've got plenty of time. Gives you 2 hours, I think. Yeah, 2 hours to take the test. And take it at a time when you're rested. And note that it's all set. Okay? Thank you very much. Take care. Good luck. Do well.